In this chapter, we introduce a physical quantity that may be mathematically unfamiliar to you. It should be physically familiar as it appears in everyday life, but you may not have thought about it in quite the way we're going to discuss it here. The physical quantity we're going to describe is a vector. This is a quantity having both magnitude and direction. The laws of physics require us to perform all the basic arithmetic operations with vectors, that is, addition, subtraction, multiplication, and division, that we are accustomed to performing with numbers. Extending these operations to vectors is straightforward with respect to some operations, and not at all with respect to others. In this chapter, we introduce some basic vector notation and the more straightforward arithmetic operations in section 2.1, and then discuss vector representation in Cartesian coordinate systems. By Cartesian coordinate systems, we mean an xy system in 2 dimensions, which we'll talk about in section 2.2, and an xyz system in 3 dimensions, which we'll talk about in section 2.3. The final 2 sections of this chapter deal with the less obvious arithmetic operations involving vectors, specifically the multiplication of one vector by another. As it turns out, there are infinitely many ways we might define what it means to multiply 2 vectors together, but fortunately there are just 2 operations that end up being useful and physically meaningful. These are the dot product, discussed in section 2.4, and the cross product, discussed in section 2.5. One more issue bears highlighting before we begin. In the first section, you'll notice that we focus on a geometric representation of vectors. This should be familiar from geometry and trigonometry, and it is also easy to visualize. It turns out, though, that a geometric approach is not particularly efficient and also becomes very difficult to visualize as we transition to arbitrary problems in 3 dimensions. For this reason, you'll notice that we transition away from a geometric approach and towards a set of rules we'll call vector operations as we move towards the end of the chapter. This latter approach isn't easy to visualize, but that is precisely the point. In problems in 3 dimensions, we want to be confident in our operations without having to be able to see the relationships between the vectors. We make a distinction between physical entities that have just a magnitude versus those that have magnitude as well as direction. In mathematics, numbers have only a magnitude, whether those numbers are integer, rational, or irrational numbers. In physics, entities having just a magnitude are defined as scalars. Scalars are to physics as numbers are to mathematics. Mass, for example, is a scalar inertia. If you have ever rearranged a room full of furniture, you have a visceral appreciation of the lack of a mass's direction. It doesn't matter which direction you push the furniture around the room, as long as the flooring doesn't change from one location to another. A piece of furniture offers the same resistance to acquiring linear motion, no matter what direction you push it. Its translational inertia, which is to say its mass, has no dependence on direction. In contrast, the weight of that same piece of furniture absolutely has a direction, down, in addition to a magnitude. It's also the case that the direction the furniture moves absolutely depends on the orientation of the force you apply as you push it. Forces have direction in addition to magnitude and are therefore vectors. It turns out that having direction as well as magnitude is not quite sufficient to define something as a vector. It also has to obey certain transformation laws. This last requirement presents itself in some branches of mechanics, but not in statics, so for now we'll just say that a physical entity having direction as well as magnitude is a vector. There are many ways of representing vectors in written texts. 2 of the most common are placing a little arrow over the symbol or writing the symbol in a bold-faced font. In the examples we'll discuss in these videos, I'll use this first approach. The magnitude of a vector is frequently written by placing vertical bars around the vector. This is a lot of extra notation, so I'll just use the symbol itself to indicate magnitude. That is, if I simply write a vector quantity like this, that will indicate a magnitude versus writing it as the symbol with the arrow over the top, and I'll use just a single arrowhead instead of a double arrowhead. This will indicate a vector. There is more than one way to specify the direction of a vector. The two methods shown here are adequate for two-dimensional representation, but not for three-dimensional. The polar vector representation specifies the angular displacement from a specified axis. Suppose we pick the reference axis as the positive x-axis, as is often the case. In 2D, this specifies a unique direction. In 3D, it's not so simple. An angle theta defined off the x-axis might be defined off the xy plane or might be defined in the xz plane. In fact, there is a continuum of lines off the x-axis that represents a prescribed angular displacement, the locus of which is a conical surface. In 3D, the polar vector representation is not unique. There is a similar non-uniqueness in 3D when we specify the location in a north, south, east, west Cartesian coordinate system. Here, the locus of points satisfying the specified direction consists of a line perpendicular to the xy plane. A more common approach for specifying direction involves the use of unit vectors. Here we write the vector with its magnitude and direction partitioned like this. We say vector f is a magnitude f on a unit vector. So the magnitude is here, and the orientation or direction is here. The magnitude contains the dimensions of the physical quantity. For force, F has dimensions of pounds in English units or newtons in SI units. The unit vector is designated by placing a hat or a caret over the symbol instead of the arrow. It is called a unit vector because it has a magnitude unity or 1. It is also dimensionless. You can think of a unit vector as a pointer. Its sole purpose is to provide orientation. Unit vectors can be expressed as combinations of other unit vectors. We define special unit vectors attached to individual coordinate directions. In 3 dimensions, we define I, J, and K as unit vectors aligned with the x, y, and z coordinate axes respectively. Let's go back to our furniture moving exercise. Suppose we define a Cartesian coordinate system with the xz plane coincident with the floor so that the y-axis is in the vertical direction. In this case, we would represent the weight as a scalar magnitude equal to the mass times the gravitational constant on a direction which in this case would be in the minus j direction. We will return to unit vectors a little later. For now, you should make a note that this method of vector representation is as useful in 3D as it is in 2D. Some aspects of vector terminology are straightforward. Here we have a velocity vector in the xy plane. The direction of the vector is from the tail to the head, so this velocity moves up and to the right. If we wanted to specify motion in the opposite direction, the head and tail would be interchanged to indicate motion down and to the left. The precise location of this vector in space is indicated by its line of action. We could imagine filling this space with a continuum of lines parallel to the given line of action, but a specific trajectory could only be obtained by beginning from a specific starting point on a unique line of action with a given velocity. Lines of action are particularly important in equilibrium. We will see that the effect of a force on a body is unchanged if we slide the force along its line of action, and it is often convenient to slide forces along their lines of action performing vector operations. Displacing a force from its actual line of action, that is, picking it up and placing it on a parallel line offset from the original line of action, changes some aspects of the force's influence on the body and is not generally permitted without compensating for that displacement. Circumstances under which forces can be displaced from their original line of action are discussed further at the end of Chapter 4 in the section on equivalent force systems. We turn now to two of the simpler arithmetic operations involving vectors, addition and subtraction. Here we have two vectors a and b, and we want to find the resultant r from adding a and b together. This is an important operation in imposing force equilibrium. In performing this operation, you will notice that we will be picking vectors up from their original locations and placing them at other locations. This is in direct contradiction to what I just said in the previous slide about not displacing force vectors from their original lines of action. But it turns out that in the case of finding a resultant force, this procedure is acceptable. We begin with original vectors a and b in the upper left-hand corner. The slide shows three different ways of producing a resultant, all with identical results. In the upper right figure, we have picked up a and placed its tail on the tail of b. This tail-to-tail addition is also called parallelogram addition. If we strike off a line parallel to a at the head of b, and then strike off a second line parallel to b at the head of a, we form a parallelogram. The resultant r is the diagonal along the parallelogram with a tail coincident with the tails of a and b. The lower left and lower right figures show two different head-to-tail additions. In the lower left figure, we have picked up b and placed the tail of b at the head of a. The result is the vector whose tail is coincident with the tail of a and whose head is coincident with the head of b. A complementary operation is shown in the lower right figure. Here we have picked up a and placed the tail of a at the head of b. The resultant is the vector whose tail is coincident with the tail of b and whose head is coincident with the head of a. These operations show that we get the same resultant independent of the method and order of addition. This is expressed in the commutative law r equals a plus b equals b plus a. This is also one of the additional mathematical requirements for a physical entity to be defined as a vector. It must have direction, it must have magnitude, and it must obey the commutative law in addition. Vector subtraction can be thought of as a combination of vector multiplication by a scalar and vector addition. First, consider multiplication of a vector by a positive scalar s. Multiplication of a vector by a scalar produces another vector in the same direction but with a new magnitude. If s is greater than 1, the vector is lengthened. If s is less than 1, the vector is shortened. If the scalar is negative, its direction will be reversed, that is, the head and tail will be interchanged, in addition to its magnitude being changed. If we multiply the vector by scalar s equal to -1, the vector's direction is flipped without changing its magnitude. As shown in the middle of this slide, the subtraction of b from a can be thought of as the addition of -1 times b to a. We will look at some examples of vector addition shortly. As mentioned in the opening slide, our initial techniques will be visual and rely on geometry and trigonometry. This will be fine for two-dimensional problems, but eventually we will need to transition to more efficient operations. Although our initial illustration involved the addition of two vectors, resultants can be defined from the addition of an arbitrary number of vectors. This slide shows the two combinations of adding a plus b head to tail, as well as 3 of the 6 permutations for adding a, b, and c head to tail. The shapes formed by the addition of these vectors are generally referred to as vector polygons. The simplest of these results from the addition of two vectors and produces a triangle. Since we have familiar relationships from geometry and trigonometry to help us, it is sometimes useful to find a resultant as a sequence of operations involving the addition of two vectors. Referring to the lower left figure, we could, for example, define an intermediate resultant Q resulting from the addition of B to A, and then perform a second addition of the intermediate resultant Q to C to find R2. It may be easier to perform calculations with these two vector triangles than with a single vector polygon. There may be other instances, however, when a sketch of the whole vector polygon provides more valuable insight into the solution of a problem. We'll look at examples of both shortly. Before proceeding further, we'll remind ourselves of a couple of relationships from geometry and trigonometry that we'll use repeatedly. You will not be asked to prove or derive these expressions, although it doesn't take a great deal of work to do so. Given a triangle of arbitrary shape and sides of length A, B, and C, and angles opposite those sides of theta A, theta B, and theta C respectively, we have these two laws, the law of sines and the law of cosines. We have written just one of the relationships involving the law of cosines, but we could fill in the other two if we wanted. Lengths A and C, and we knew theta B, we could find the length of B from writing B equals A squared plus C squared minus 2AC cosine theta B. In the limit that one of the angles, say theta A, becomes 90 degrees, we have a right triangle, and sine of theta A equals sine of 90 degrees equals 1. We can see directly then from the law of sines that we get that B is equal to A sine theta B, and that C is equal to A sine theta C. Because the triangle is now a right triangle, it is also the case that theta B and theta C are complementary angles. That is, theta B is 90 degrees minus theta C, and that means that sine theta B is equal to cosine theta C. Note that this is also consistent with the definitions of sines and cosines in a right triangle. We know that in a right triangle, the sine of the angle theta C in this case is defined as the ratio of the opposite to the hypotenuse. And since the opposite is C and the hypotenuse is A, it follows directly that C is A sine theta C. Cosine theta C is defined as the ratio of the adjacent to the hypotenuse, and since I already have A for the length of the side here, I'll just go ahead and write ADJ for adjacent over the hypotenuse. And since the adjacent in this case is B, we have directly that B is equal to A cosine theta C. These results are also consistent with the Pythagorean theorem, since B squared plus C squared would be equal to A squared times the quantity cosine squared theta C plus sine squared theta C. And this is identically equal to 1. So we have B squared plus C squared equals A squared. If any of these results are foreign to you, you should immediately review basic geometry and trigonometry before proceeding further. These subjects, along with basic algebra, constitute the bulk of the mathematical tools you will need for most problem solving in statics. We will use some calculus late in the course, but we won't need it until we get to Chapter 7. For now, geometry, trig, and algebra are the tools you'll need, and we expect you to be proficient in these areas.